AES, or Advanced Encryption Standard, is a symmetric block cipher widely used on the Internet in protocols like HTTPS, VPN, and Wi-Fi security. You might think that its algorithm must be very complex, but basically it's just a series of substitutions and permutations. Let me explain it to you in the next 6 minutes. We say it's symmetric because it uses the same key to encrypt and decrypt a message. Block cipher means it operates on a sequence of bits with a given length. For AES, that fixed length is 128 bits. Your plain text input is cut into 128-bit long pieces, and AES works on them one by one. AES requires your key to be either 128, 192, or 256 bits. In this video, I'll use a 128-bit key as an example. So now we know that for each block, AES takes in a 128-bit plain text and a 128-bit key, runs an algorithm, and outputs a 128-bit ciphertext. Now we want to ask, what exactly is that algorithm? The best way to grasp the big picture of AES is to look at its pseudocode presented in its specification. For encryption, the main function is called cipher. It first expands the provided 128-bit key into 11 different round keys. Why 11? Because the cipher function for a 128-bit key has 10 rounds, and a new round key is used each time the add round key method is called. That happens once at the start, once at the end, and 9 times inside the main loop. Apart from add round key, the key isn't directly passed to the other methods. These methods are designed for diffusion, which means spreading even a single bit change in input to many more bits in the output ciphertext. Before we dive into the methods, let's look at the data structure first. The state is made of 16 bytes, or 128 bits. In memory, it's just a flat array, but the specification displayed it as a column-based 4x4 array. Most operations read and update data column by column, working with 4 bytes at a time. Simple enough, right? Let's keep going. The first method is subbytes. It replaces each byte in a state independently with another value based on a lookup table. This provides a 1-to-1 mapping for any 8-bit number. This lookup table isn't arbitrary, it's mathematically based on the Galois field on 2 to the power of 8. While that's out of scope for this video, what's important is that it provides a high degree of non-linearity. It's not like simple operations like replacing 1 with 2, 2 with 3, which was very linear. Another key property is that this lookup table is naturally invertible, making it easy to reverse the replacement during decryption. The next method for diffusion is shift rows. This is the most straightforward one. It shifts each row by a different offset. The first row has no shift, the second row shifts 1 cell, the third row shifts 2 cells, and the fourth row shifts 3 cells. The next one is mixed columns. This transformation multiplies each of the 4 columns of the state by a single fixed matrix. If you look closely at each column of this matrix, they are all just rotations of the values 2, 1, 1, 3. In case you are not that familiar with matrix multiplication, I'm showing you how this matrix mixes these columns. Okay, that's all for diffusion. We can finally talk about how the key is involved. Besides the state, add round key also takes in a 16-byte round key. It simply XOR the state and the round key column by column and writes the result back to the state. Remember that we have 11 round keys for AES 128, which means 11 calls to add round key, each with a different round key. These 11 round keys are generated by the key expansion method. This method takes your original 16-byte key and appends 10 more generated keys to the array. The principle behind this key generation process is confusion, which means even a single bit change in the original key should affect many bits in the generated key and the generated ciphertext. Here's how it's done. Once again, it works column by column. Each new column depends on 2 other columns. The very last column, I-1, and the column from the last key at the same position, which is I-4. The process is more complex for the very first column of each round key. It takes the last column, rotates it by 1 byte, runs it through the same subbyte substitution box, then XORs it with both a round constant and a column at I-4. For the second and all other columns in each round key, it's much simpler. You just XOR those 2 existing columns. This process is repeated 10 times. And then we're done with key expansion. Now let me show you how much confusion we have achieved. Let me change the first bit in the original key, and here are the affected bytes. Great! Now we've covered all the main parts of the encryption process. Hopefully you have a good idea of what's going on. Since the encryption process is quite similar, I'll show you the pseudocode as well. The code structure looks exactly the same, but in reversed order, and each method has its inverted counterpart. Inverted shift rows shift the same amount of cells as in shift rows, but instead of to the end, it moves cells to the start of each row. For inverted mixed columns, we just replace the fixed matrix with its reverse matrix and update the state column by column. Inverted subbytes use the reverse lookup table, which is easy to derive, and that's all methods that has inverted version. Note that add around key is its own inverse, since it's just a simple exclusive OR operation. Okay, that's all for the AES block cipher itself, but not the end of the story. In real world, when you want to encrypt data with AES, you also have to add a postfix like GCM, CBC, CTR. Those are called block cipher mode. They also matter a lot to security and have an interesting history. I'll talk about it in the next video. Thanks for watching, and please subscribe to my channel if you like the way I unveil tech details. See you in the next one.